So dear students, in this video we are going to cover the left out part of our chapter number 1. As I have told you that I have left one lesson which I would have done before the Gauss's law application, but even then it doesn't make any much difference, so I'm going to discuss that left out topic right now. And the topic for today's discussion will be continuous charge distribution. So see this particular two words, that is continuous charge. What we have discussed in earlier classes was in any body, if it is a charged body, let us take if it is a charged body, what we have concluded was this charged body this charged body is made up of collection of discrete charges. This particular charged body is a collection of discrete charges, which means there exists an infinitesimally smaller charge entity which cannot be further divided. So this body is a collection of discrete charges, and there exists an infinitesimally smallest charge entity which cannot be further divided, and we have given that particular smallest entity a name, and that is known as your electric charge, which is represented by symbol E. That means this electric charge E is the smallest charge possible in any body or in the universe itself. This particular charge cannot be further divided into smaller charges. That means any charged body is an integral collection of this particular electric charge. So from this particular discrete nature of charges, we have theorized our quantization of charges, which means every body contains a charge which must be an integral multiple of this particular electric charges, where n is your integer, and which can have both positive as well as negative values. So this was known as our quantization of electric charges. So earlier what we have discussed was this particular concept, which tells us that every body is made up of very smallest collection of very smallest unit of charges, which in group or which together makes a larger charged body. So it is similar to see as suppose you have a straight line. So you see this straight line to be continuous. If you see physically or macroscopically, you see this body to be continuous body, because this straight line is a continuous line which do not have breaks in them. But in actually, if you zoom in any portion of this straight line, what you will see is this particular straight line is made up of actually very small smallest dots possible. So the smallest dots makes a continuous straight line. But in reality, these dots are discrete in nature. They have a space in between them. So what I want to conclude is, in reality, your charge also behaves like this. They are actually the collection of the smallest entity, which is known as electric charge. But when they reside in any body, they become continuous, or we treat them continuous, because macroscopically we cannot see those smallest entity with our naked eye. That's why every body we treat them to be continuous body. Another example is human body. Another example will be human body. Human body is actually made up of very indivisible cells. These are human cells, which makes up the skin, or human body, which makes up human body. And you know, human body is a continuous body. You don't see any holes or pores or breaks in a human body, but actually they have the cellular gaps inside a human body, but we cannot see through our naked eye. That's why when we see a human body, we see it to be continuous. That's why we treat a human body to be a continuous body. Similar manner, in the similar manner, every charged body is treated as a continuous charged body, even if it is made up of very indivisible quantized electric charges which have a gaps in between them. But even then, we treat them to be continuous charged body or continuous charge distribution. So first, in this discussion of continuous charge distribution, so our first discussion is linear charge distribution. Linear charge distribution. Linear charge distribution. So linear means, it is a mathematical term which means line or a straight line. So linear is a line. So line charge distribution. That means, suppose you have a straight wire, so it is a line kind of thing. So if you have a straight wire, if this is made up of charges, which we treat them to be continuous, so this charge, linear charge distribution, this is a wire. So this wire is made up of charges. So this particular distribution is known as linear charge distribution. A charged straight wire is an example of linear charge distribution. Linear charge distribution. So any charged body which is straight or which is very thin and which is very much elongated, such kind of distribution are categorized in linear charge distribution. And we define a quantity related to this linear charge distribution, and that is your linear charge density. That is known as linear charge density, which is nothing but linear charge density can be defined as total charge which is represented by lambda. Linear charge density is represented by lambda. So linear charge density, that is lambda, is total charge contained in this particular charge body. If Q is the total charge contained in this charge body, and if L is the length of this particular wire, then Q by L will be your linear charge density. That is total charge contained divided by the length of the wire, or any long straight thing is known as linear charge density. And remember, for any linear charge distribution, for example this particular wire, it do not have any cross-sectional area. So any linear charge body do not have cross-sectional area. Its cross-sectional area is 0, or it's not. It is neglected. so do not have cross-sectional area. So that's why it has only a length. So its linear charge density can be defined as total charge contained in the wire divided by the length of the wire. Another charge distribution is your surface charge distribution or surface charge distribution. So surface charge distribution is basically if you have a surface, suppose you have a sphere or a cylinder which have its curved surface. So suppose you have a sphere, for example, and its surface area, curved surface area is full of charges, then we treat this particular charges to be continuous in nature, and this particular system is known as, or this particular distribution is known as surface charge distribution. And suppose A is the surface area of this particular sphere, then we can define surface charge density of this particular sphere or a surface, and that is denoted by your sigma. So sigma will be, if Q is the total charge contained on this sphere, then Q divided by the area of the sphere is your surface charge density. Linear charge density, unit of linear charge density is Coulomb divided by length, that is your Coulomb is Coulomb, just length is in meter, so Coulomb meter inverse. Similarly, its unit will be Coulomb meter inverse 2. Similarly, you have third kind of distribution, and that is your volume charge distribution. So you can define it in the similar manner, distribution. So which tells me, if you have a system, bulk system, whose entire volume is occupied by the charges, then entire volume is, if V is the volume of this particular system and if Q is the charge contained in this system, then we can define a quantity related to this particular volume charge distribution, and that is your volume charge density. Volume charge density, and that is denoted by your rho. So rho will be equals to charge contained in the volume divided by the volume of the body itself. So this is your volume charge density, and its unit will be Coulomb meter to the power minus 3. So these are all the discussion that are needed to be done in this particular section, and I think this is enough for you for this level to carry forward with all the concepts related or which require this particular concepts. So this is it. Now what I want you to do is so this is the end of our, so this is literally end of first chapter. So what you do now is you complete or solve the numericals from your NCERT book itself. And I don't mean by like complete means you have to do all the numericals. You just do those numericals which you are confident with, or you think that you can do those numericals. It is not necessary that you are required to understand or you are required to complete all the numericals. So do few numericals which you think that that will be solvable for you. So this is it. Now from tomorrow we are going to start a new chapter, and that chapter is our electric potential and capacitance. That is chapter 2. So from tomorrow we are doing chapter number 2, that is electric potential and capacitance. So I hope you guys are understanding or grasping the concepts. It is difficult for even for you to understand in videos that I'm providing you. It is very hard to grasp. It is not like it will not be like in classrooms, but still you have to work hard, or you have to concentrate, focus. You have to research, or you have to refer other books also. If this videos are not, this video will not be enough for you, so you have to refer other books, other videos from YouTube, and such that you can grasp and understand more and more confidence. So I hope you're trying your best, you're making notes, and you're enjoying what I'm doing here. So I hope you will continue to follow this kind of teaching, because we don't know when is our school going to reopen. We are not sure at this moment, so this will be our way of teaching, quite for the future, quite more for the future. So that's it. So study well and do all the numericals. So meet you in the next video. That will be our next chapter. Thank you.